difference can be defined with again the CIP sequence rule, and this is what we discussed last time, right? You can identify the lowest priority group, right? Assign 4, right, for that, and then without that, right, you can locate the lowest the priority group, the backward. Then with 3 other groups, you can formulate a triangle. With which you can decide the clockwise versus counterclockwise directionalities. So for instance, in this case, from 1 to 3, you can make the clockwise rotation. That's why this absolute configuration is right? Whereas for this triangle, you can make the counterclockwise rotation from 1 to 2, 2 to 3. Right? And that's why this asymmetric center signed as an S absolute configuration. Okay? That's how we define R versus S. So you can then designate, right, R versus S in this case. In this particular case, you can rationalize this as the dimensions to each other, right? So if this is S, right, that means this asymmetric center has to be R, right? So S and R, R versus S, let's formulate the pair of dimensions. That's what we studied, and this is a one way you can invert or draw the pairing ensuring. So let's say you have, right, this absolute configuration. Perhaps you can assign, right, R versus S configuration, the absolute configuration for this asymmetric centers. Right? But what you are treating here is just switching this methyl number 3 substituent and hydrogen number 4. Right? Then as we discussed last time, they will make the absolute configuration, right, inverted. Right? And then if you measure or identify the absolute configuration of this asymmetric centers, which is R, by the way, right? Then automatically know that this has to be S, right? Because you treated, right, this process. You convert just to or swap 2 substituents, right? That will give rise to the inversion of the absolute configuration. Right? You can do rotation in your head and rationalize what this should be the case, but you can basically utilize this process, right, to draw the enantiomer, just swapping 2 substituents. Right? That will give rise to the inversion of the absolute configuration. Okay? 그래서 저희가 지난 시간에도 한번 언급을 했었고 지난 시간에도 이야기했듯이 이넨시오머 관계를 뭐 찾아야 될 때도 있고 그리셔야 될 때도 있겠죠, 그렇죠? 요게 하나의 컨피규레이션 주어졌다면 거기로부터 스와핑 2개의 서브스티튜트를 그냥 교체만 하게 되면 그 작업이 어떤 결과를 야기하는 것이냐면 absolute configuration inversion 되는 결과를 야기하게 된다. 그래서 인버전을 시켰더니 이제 요 4번 lowest priority 그룹이 뒤로 빠져 있잖아요. 그러면은 이렇게 3개만 가지고 삼각형을 그렸을 때 clockwise, counterclockwise rotation을 이제 정하시기가 좀 수월해지겠죠. 맨 뒤에 그룹이 뒤로 가 있으니까 O, 에틸의 카본, 메틸의 카본이니까 이렇게 돌아가겠죠. clockwise rotation이니까 이 카본의 absolute configuration, asymmetric center의 absolute configuration이 이제 R이 되는 것이고, 그러면은 바로 자동으로 inversion 전에 요 absolute configuration 카본의 asymmetric center 카본의 absolute configuration의 S임을 이제 아실 수가 있다. 이렇게 이해하시면 되겠습니다. 그래서 2개의 substituent를 swapping하게 되면 그 absolute configuration, asymmetric center의 absolute configuration inversion 된다. 이거를 기억하시면 되겠습니다. 이 룰은 저희가 또 지난 시간에 배웠던 Fisher projection도 그대로 적용이 됩니다. 그래서 뭐 본인이 공간 지각 능력이 뛰어나셔서 그냥 척 보고 삼각형을 찾을 수 있고 머릿속에서 구조가 잘 돌아가시면 이런 프로세스 안 택하셔도 돼요. 근데 약간 나는 직관적으로 공간적으로 잘 이해가 안 된다, 안 그려진다 이러시는 분들은 기계적으로 적용하시면 된다라는 이야기입니다. 제일 lowest priority 그룹이 뒤로 빠지게 substituent 2개를 swapping을 하시고 그러면 그 뒤에 빠진 애를 빼고 나머지 3개 가지고 삼각형의 방향성을 결정하시면 이제 RS 캐릭터를 결정할 수 있습니다. 있을 것이고 인버전을 뭐 한 번 했다, 뭐 두 번 했다, 그거를 이제 고려하셔서 원래 오리지널 구조의 Symmetric Center의 Absolute Configuration을 identify 하시면 되겠다. 그렇죠? Right, and we also discussed the Fisher projections, and you may find this cross type representation. This is called the Fisher projection we discussed last time, and this illustrate these three equivalent presentation-based claims. So 2 and 4 in the horizontal location, these option 2 and 4 are base plate, it's existing towards yourself, the viewer out of the plane, whereas 1 and 3 they are protruding in or getting inside of a plane. So you can then imagine there is a 3D structure, formulate this architecture configuration, in other words, so with this visual projection, you can then rationalize, this type of 3D equivalent presentation. Then you know that the lowest priority group hydrogen in this case is existing in a backward. So with which you can just decide the directionality of this triangle. So chloro, propyl, and ethyl, clockwise. That's why this is R, And you can do the same thing for the enantiomer, This is the lowest priority group hydrogen, Existing backward. So we can define this triangle and decide the directionalities, The chloro, propyl carbon, and ethyl carbon. So this will give you the counterclockwise rotation. That's why this is S. You can do the same thing for the bottom one, and we can identify S versus R character. Yeah, and there are some tricky cases, not tricky case though, but you can assign priority. In this case, you have the double bond, in this case, since we are using the same rule, the sequence rule, you can treat it this or think about this. It's equivalent to the bonding network like this. This carbon has two single bond with oxygen, when you have the double bond. And you can also think about, in terms of like this oxygen perspective, this oxygen also have two bonds, with carbon. So you can unravel this relationship, the bonding network like this. What about double bond between carbon? You can dissect and then encode, or think about this as equivalent to this type of bond. So this carbon has two bonds with carbon, And also this carbon, You need to think about from the perspective of this carbon. This carbon also has, two double bond with carbons. What about the alkyne, containing triple bonds, So you can think about then this carbon here has three sigma bond with carbon, single bond with carbon in other words. So that's why this has 1, 2, 3. You can also think about from this carbon as well, And this carbon also has to have three single bond with carbon. So you can double check 1, 2, 3. That's how you can encode and decide. And in a tricky case, you should do that, Assign priority. This is what we discussed. You can assign priority in order of decreasing mass numbers. So here we're comparing hydrogen deuterium group, And priorities follows, Higher the mass number, the higher the priorities, less number, 1, 2, 3, meaning, this one, the highest priority among this class. And this is the what we already discussed, But give you a different image, How to assign R versus S or S versus R, Absolute configuration. So let's say you have the enantiomer A and you have lowest priority group hydrogen, which is 4 here. And if your eyes seeing the molecule in this direction, then you can identify this triangle, And you already assign priority, O H, right, oxygen, carbon in ethane or ethyl group, and carbon in methyl, with which you can make the clockwise rotation. Right? That's why this should be R, right? And you can also think about the enantiomer of that, right? And then this side, right, the directionalities, right? And this will give you eventually S, right? Okay, that's what we all discussed, how to labeling or identify, right, the absolute configuration of the asymmetric center, right? or stereogenic center in this case as well. Right? 그래서 다 동일한 방식이 적용되는 거예요. 이 어디셔널 슬라이드는 이제 다른 텍스트북에서 제시한 이미지를 좀 가져와 봤어요. 이제 조금 더 참고하시라고. 근데 다를 게 없습니다. 1, 2, 3, 4 RB로 잘만 디파인 하실 수 있고 4번을 맨 뒤로 뺀 다음에 1, 2, 3 가지고 방향성만 결정하실 수 있으면 R, S 결정하실 수 있겠죠. 그렇죠? Okay, this is what we already discussed. When you switch for the two substituents, then revert the absolute configuration S to R to S. Okay? And perhaps you can solve these problems, right? So why don't we try? So basically, you can apply the same rule, right? Same sequence rule you apply for EG nomenclature. Right? So it's basically the same practice. So I'm sure you guys can solve this one, and you can try to maybe solve the bottom one as well. Sin R versus S configuration. Maybe we can try some of the down below, right? So what is the absolute configuration for this asymmetric centers, right? And then maybe we can apply the trick we just learned, right? In this case, you know that there is a hydrogen actually protruding out of the plane, right? So trick, if you apply the trick, if you can solve in your head, right, with the rotation and the sign, that's fine. But if you want to treat it as a applying the trick we just learned, right? You can then swapping this too. Right? Then you can generate the enantiomer, right? And this will give you this one, right? What we did is simply swapping this, and this will create or give rise to an enantiomer, right, of the left, to the right. And then you know that this force priority group hydrogen is now just protruding right in the plane. So what you can decide then directionality in this triangles. Right? If you have top priority here, second priority there, third priority here. Right? But once you can make the counterclockwise rotation, that means this asymmetric center has to S. Right? Automatically, then this one has to be R. The original structure or configuration is left hand side, you can answer R. That's one trick you can apply. And this one is easy. You already have the orientation or configuration, right? Hydrogen backward. So you can make a triangle like this, and then what you can do is assigning the priority 1, 2, 3. Okay? But once you can make the clockwise rotation, it has to be R. Okay? What about this one? Right? You can make the triangle with this, right? And this side rotation, if you can see this, right? Projection. Then this is top priority, second, third priority, right? So this will give you clockwise rotation, right? This has to be R. What about this one? Right? You can see this molecule from this perspective, and you can make right, this triangle and this side directionality. So if this is some conversion, right, then you can swap two substituents, right, to make the lowest priority hydrogen goes backward from the normal projection, right? So maybe you can think of swapping this to hydrogen and methyl, right? And this will give you this, right? Solid wedge, this, right? Then you can define triangle with these three, right? And you can assign priority 1, 2, 3, right? And this will give you counterclockwise. So the asymmetric center, this one has to be S, right? That means the original configuration, it's asymmetric center, right? It has to be R, right? You can double check. You can solve or assign R versus S configuration in 2 ways maybe, and then compare the answers. That's how you can maybe double check. 그래서 solid wedge, hat wedge presentation 가지고 3D configuration이 머릿속에서 그냥 쉽게 그려져서 priority group assign하고 rotation이 그냥 바로 직관적으로 보이시는 분은 바로 assign 하셔도 되고, 그렇죠? 그게 잘 안 된다. 그러면 제가 말씀드린 것처럼 2개를 스와핑을 해서 이넨시오머 구조를 만들고 이넨시오머를 어사인한 이후에 원래 구조를 이제 다시 한번 인버전 시켜주는 식으로 원래 컨피그레이션에 제로 케미스트를 어사인하실 수도 있다. 2가지를 다 해보는 걸 추천드려요. 그래서 답을 한번 더블 체크하는 효과도 있고, 그렇죠? You can do the same thing with the Fisher projections, right? And I'm sure you can solve this one as well. So you can think about this right cross limitation. The Fisher projection illustrate the 3D equivalent like this, right? Then it's better, right, to locate the force priorities, the lowest priority groups, protruding in, right, to the plane. So this case, right, the methyl is the lowest priority group immediately, right? Then you can decide. You can define triangle with this 3. Then if you know the priority sum of these 3, then you can decide the direction on this, right? So let me see. This is Bruno group, right? And this is 2 methyl, so 1, 2, 3, right? So this will give you the counterclockwise. So this is makes better after the configuration has to be this. Okay? And you can apply second rule, and if you need the swapping, right, then you can do that, right? You can locate, for instance, this case, right, by swapping this 2, for instance, right, then you can create the enantiomer, right? Then you triangle in this 3. Okay? And you know the priority. This will give you R configuration. That means the original asymmetric center, original configuration has repeats. 피셔 프로젝션에서도 마찬가지고 두 그룹을 스와핑하면 absolute configuration이 inversion 된다라는 아이디어를 가지고 여기다 뭐 1번이나 3번 뒷자리로 가게 4번 priority를 위치시키면 되겠죠. 그 다음에 삼각형 나온 거 가지고 삼각형 디렉셔널리티를 정하시면 스와핑한 이후에 asymmetric 센터의 configuration을 아실 것이고 그거에 맞춰서 오리지널 configuration의 R escalator를 결정하시면 됩니다. Okay? Right, thus far we have discussed these few isomers. The isomer with single chirality center, asymmetric center in other words, but we can think about the isomer with multiple chirality centers. So, for instance, this molecule has 2 asymmetric centers. Okay? And then in this case, you have to define the relationship, unique relationship. It's called the diastereomer relationship. So a molecule with n stereogenic center, n asymmetric centers, in other words, right? In this case, the maximum number of the stereoisomer is 2. Okay? So if you apply 2, for instance, right, to the n, then you get 4. That's the maximum number you can expect from the molecule containing 2 asymmetric centers. That's the maximum numbers, right? And this is the example, the possible stereoisomers of 2,3 dibromo pentane, right? So this is a pentane. You have 1, 2, 3, 4, 5 carbons, right? At 2 and 3 position, you have bromo group, right? In this case, you can identify this 4 different stereoisomers, and then you can define the relationship right among this, right? So A and B, they are an enantiomer relationship. C and D, they are also the enantiomer relationship, right? Then what happened, right? What about the relationship between B and C, right? Or A and D? For that, we can define the diastereomers. So here is the definition of the diastereomer, right? The diastereomers are stereoisomers that are not mirror image of each other. 그래서 한국말로 하면 뭐 부분 이체 이성질체라고 부르죠, 그렇죠? 그래서 거울상 이성질체, 이네이셔너 관계가 아닌 이체 이성질체 관계를 저희가 다이아스토머라고 일반적으로 정의할 수가 있습니다. 그래서 asymmetric center, 뭐 stereogenic center라고 불러도 뭐 무방하겠죠. asymmetric center가 이제 n 개인 분자의 경우에는 maximum 넘버로 2의 n 승계의 stereoisomer을 볼 수가 있고, maximum이라고 이야기하는 거는 뒤에서 저희가 또 매주 컴파운드라는 거를 다루게 될 텐데 항상 2의 n 승계는 아니기 때문에 저희가 maximum 넘버라고 부르는 거예요. 그래서 2,3 다이브로모 펜테인을 보면 이제 2개의 asymmetric center가 있으니까 각각의 이제 2가지 possibility가 존재하고 absolute configuration R 혹은 S니까 뭐 조합의 문제인 거죠. 2 곱하기 2 하면 4가지가 가능한 거죠. R, R, S, 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 R 이렇게. 뒤에서 또 다루겠지만 그들 사이 이제 관계를 봤을 때 R, R, S, S가 되면 뒤에서 또 보겠지만 이제 이네이셔너 관계가 될 것이고 S, R, R, S로 이네이셔너 관계가 될 것이고, 그렇죠? 뒤에서 조금 더 그 관계에 대해서는 자세하게 다룰 텐데 일단 여러분들이 2개가 있을 때 이네이셔너 4개를 스테레오아이소머죠. 스테레오아이소머 4개를 그릴 수가 있어야 되고 A, B, C, D 요 각각에 대해서 이제 거울상 이성질체 관계냐, 부분 입체 이성질체 관계냐 를 이제 어사인 하실 수 있어야 됩니다. 그 트릭에 대해서는 이제 또 뒤에서 말씀드리도록 하겠습니다. Okay. So again, diastereomers or the stereoisomers, they're not mirror image of each other. Right? In this case, A and B, they are mirror image to each other. C and D, they are mirror image to each other. What about B and C? They are not the mirror image to each other. Right? In this case, we can define B as a diastereomer to C, or C is a diastereomer to B. Right? That's a relationship. Right, so we can think about the relationship a little bit more, right? We can think about more quantitatively. right? So when a compound has more than one stereogenic center, or asymmetric center in this case, right? R and S configuration must be assigned to each of them. For instance, you can assign, right, absolute configuration here, which is S, right? You can double check why this is S, right, for your practice. And this is the R. Okay? And again, these two are the asymmetric centers, right? And this is the one stereoisomer of 2,3 diagonal pentane, right? And then you can make a full name, the complete name for this as well, right? With the parenthesis and assign the character, right? The absolute configuration, right? And 2 position S, 3 positions R, right? That's why you have to specify inside the parenthesis 2S comma 3R, right? And you can connect with the hyphen and the original name, 2,3 diagonal pentane, right? So with this, right, specification, you can designate the one stereoisomer, right? Right, you can take a look at the notion here. The identical compounds have the same RS designations that every tetrahedral stereogenic center, right, has to be the case, right? Enantiomers have exactly opposite RS designations, right? So, for instance, you can think about then 2R, 3S, right? 2,3 diagonal pentane, right? And these two can be an enantiomer or in a relationship as enantiomers, right? So enantiomers have exactly opposite RS designation, right? You can extend the idea of like the molecule containing one single asymmetric center, right? R to S, S to R, this will give rise to enantiomer relationship. And this can apply to the molecule containing more than one asymmetric center. What about diastereomer relationship? The diastereomers have the same RS designation for at least one stereogenic center, right? Or asymmetric center, and opposite for at least one of the other stereogenic center, right? So you can take an example, right? Maybe you can think about then 2S, 3S, right? 2,3 dibromo pentane. Right? In this case, you are sharing at least one, right, absolute configuration, and only one positions are different. Right? In this case, you can expect, right, 2S3R and 2S3S, they're going to be in diastereomer relationship. Right? So that's what the last sentence means. And this is how you can assign S versus R, right? For each asymmetric centers. So you can ignore this downside. You can just think about S1, A, B, C, D, right? This is the potential for stereoisomers for this molecule, and you can assign by yourself, right, the absolute configuration for each asymmetric center or stereogenic center, and compare, right, what the enantiomer for each case, right, A to B, for instance, the carbon here. So you can think about here as a mirror, right, and you can assign 2, right, 3 for these 2 carbon, right, and this is 2 carbon. Okay. So the absolute configuration for number 2, the left-hand side is S, right-hand side is R. And absolute configuration for carbon 3, right, is R on the left-hand side, S on the right-hand side, satisfying the enantiomer relationship. And you can, of course, right, rationalize why A and B are enantiomer to each other as well. And think about the E is now mutated, right? From this perspective. Right? You can also think about C and D, right? C, R, R, right? And D, S, S, right? Satisfying the enantiomer relationship. Right? What about between D and C, right? They are sharing one identical absolute configuration, right? So again, this is 2 and 3, right? Carbon. So number 2 carbon sharing same absolute configuration, which is R, right? But number 3 carbon, right? they do have different absolute configuration, right? Satisfying the diagonal relationship. You can basically same thing down below. You can think about the bottom one as well. Okay, 그래서 뭐 뒤에서 이제 뭐 매주 컴파운드 얘기가 나오겠지만 분자 내 구조 내 대칭면이 없는 분자의 경우에 이시메트릭 센터가 두 개인 경우를 저희가 한 개에서 두 개로 확장한 거예요, 그렇죠? 두 개인 경우를 보면 이네이쇼머리 관계, 다이소머리 관계가 네 개의 가능한 스티라이소머리에서 유도될 수가 있고, 이네이쇼머리 관계에 있으면 그렇죠? 각각의 하루는 앱솔루트 컨피규레이션이 모두 인버전이 돼요. 그래서 RR이면 SS, RS면 SR, 그렇죠? SR이면 RS 이런 식으로. 다이소머리 릴레이션십에 있으면 하나만 공유되고 하나는 다르다. 그렇죠? 뭐 이네이쇼머리 관계의 반대인 경우 여집하고 생각해보면 이해가 되실 거거든요. 그렇죠? 그래서 다이소머는 스티로 아이소머이지만 이네이쇼머리 관계에 있지 않은 스티로 아이소머를 저희가 다이소머로 정의를 했다. 그 정의를 잊지마시고 생각하시면 되겠습니다. Alright? This is same case, right? We're dealing with basically your similar molecule 3-chloro-2-butanol in this case, right? And perhaps you can rationalize, right, the relationship between each two isomer, right? 1 to 2 versus 3 to 4, right? And in this case, right, each two isomer is drawn as a staggered conformal state, right? And you can also rationalize or try to match, right, the staggered conformal or conformal structure with the future projection as well, right? So this is the future projection down below, and the above is a perspective formula, right? And you should be able to match, right? 1, right? They are same. 2, they are same. Right? 3, they are same. 4, they are same. Each you have two asymmetry centers, right? Here and there. And perhaps this is a good practice, right? To assign the absolute configuration for each quantity. And here you may notice the terminology, right? Erythro, right? And thrill, right? Here and there, right? The erythro indicate, right, in future projection, right, if the substituents are on the same side, right? Hydroxyl group, for instance, and chloro group, right, in this case, defined as an erythro entry. But if they are existing as a cross, right, relationship, in this case we define the erythro entrance. That's how you can designate erythro and thrill designation or name here. It's sort of like a conventional way in which you can define the configuration. And then when this Fisher projection is given, right, you should be able to identify the relationship, right, to each other, right? Enantiomer versus diasteromer. Okay? 그래서 Fisher projection의 적용 원리를 알고 계시다면 사실 쉽게 하실 수가 있을 거예요. 연습만 조금 되신다면 Fisher projection의 definition을 알고 계시다면, 그렇죠? 각각의 asymmetric center를 identify 하신 다음에 absolute configuration을 또 assign 하셔서 예를 들어 이 슬라이드에 있는 원 구조가, 그렇죠? perspective formula를 주어진 zero isomer과 Fisher projection과 매칭이 되는지 한번 연습을 해보시기 바랍니다. But you know, right, 1 and 2 are the enantiomer. If you imagine, right, this mirror in between 1 and 2, you can rationalize why this is the enantiomer. Right? The same thing for the Fisher projection. Imagine there is a mirror in between 1 and 2. Also think about mirror in between 3 and 4 here and there. That's how we can identify the enantiomer relationship between 1 and 2, 3 and 4, right? In both perspective formulas and Fisher projections. Right? Then you know that then, right, the isomer relationship can also test, right, in between maybe 1 and 3, right, 2 and 4, and 1 and 4. Now we are considering the special case, right? That's why you should be careful, right? Cannot just apply, right, maximum the total number of the zero isomers and right, for this case. Right? This case, right, you will encounter the major compound, right? So you can perhaps try to draw right, the enantiomer or the stereoisomers of 2,3 dibromobutane, right? So you can then first identify right the A stereoisomer, okay? And then you can identify the mirror image to that, which will be B, right? And then you can think about right the another right stereoisomer, so switching right hydrogen and bromo group on the stereogenic center, right? From A you can create C, right? And then you can draw the mirror image to that, right? You can imagine there's a mirror in between, right? C and D, right? What you can notice here is C and D are not mirror image to each other. They are actually identical. You can just rotate, right? And then they will superimpose, right? C and D, right? This ball and stick model, you can rationalize why C and D are exactly the same. But in this case, B is not the another stereoisomers, right? You can have only 3 stereoisomers in this case. Okay? So it's not 4, it's 3 when you have right the internal plane, the symmetric plane. That's what we will discuss in a few slides later. This is another projection, right? A and B, they are the enantiomer relationship. But C is called the major compound. Okay? And as I mentioned, you can identify the internal symmetric plane. Right? So if you try to draw the mirror image to this, right? C, it'll give you exactly the same one, which was D in the previous slide. Right? So C and D in this case are exactly the same. D shouldn't be the another stereoisomer. It's identical to C. Right? That's why we only have 3 stereoisomers in this particular case. Then you can think about the relationship period enantiomer, right? A and B, they are enantiomers to each other. You can also think about the relationship between A and C and B and C. Right? It's diastereomer relationship. Right? So that we can identify pairs of diastereomers here, A and C and B and C. 그래서 뭐 카이럴 센터가 이제 혹은 에이시메트릭 센터 혹은 뭐 스티로제닉 센터라고 불러도 되겠죠. 그 경우에 2개가 되는 경우에 있어서 어떤 경우에는 스티로아이소머가 총 4개, 그렇죠? 혹은 3개가 나올 수 있다. 3개가 나오는 케이스는 이제 매주 컴파운드라고 부르는 C와 같은 케이스, 슬라이드에서 보시는 인터널 시메트릭 플레인이 이제 존재하는 케이스가 될 때는 이제 C와 같이 매주 컴파운드라고 불리는 컨피규레이션 주어지게 됩니다. 이 경우에는 이넨쇼머를 그리려고 해도 결국 C와 똑같은 스피시스가 나올 수밖에 없어요. 그래서 D가 없어지는 겁니다. C와 D가 동일하다. 따라서 다른 스티로아이소머 개수를 세셔야 된다면 3개라고 답하셔야 된다는 이야기고요. 그러면 이제 구조적으로 조금 생각해 보시면 아마 답을 찾을 수도 있는데 기계적으로 또 생각을 해보셔도 되고요. 사실 인터널 플레인, 시메트릭 플레인이 있는 C와 같은 경우에 이제 아무리 거울상 성질체를 거울을 그려놓고 대칭구를 찾으려고 해도 결국 그 구조가 동일하게 된다라는 사실을 발견하게 될 거예요. 그리고 엄밀히 얘기하면 플레인 오브 시메트리 말고 포인트 오브 시메트리 포인트만 있어도 사실은 됩니다. 점대칭 구조만 분자 구조 내 존재 돌리고 돌리면 똑같아지기 때문에 뒤에서 그거는 더 추가로 설명을 드릴게요. Okay, so we discussed the major compound, right? The compound C, right? The species we discussed in the previous slide and then in this slide too, is a plane of symmetry. 대칭면이 있다는 얘기입니다. There is a plane of symmetry within, right? The configuration, and if that is the case, right, the molecule becomes the A carrier. And as a compound, generally, right, not always, but generally, in most cases, contain plane of symmetry, so that they possess two identical harmonics. You can imagine these two are exactly the same. Or, as I mentioned, right, if the molecule containing the center of symmetry, right, here, like this, right, 점대칭 구조라고 얘기할 수 있죠. 이 경우에도 AR이죠. 이거 이제 미러 이미지를 그리시려고 트라이를 해보시면 결국 뒤집어 보면 똑같아진다라는 걸 머릿속에 그리실 수가 있을 거예요. Okay, so if the compound or molecule has a plane of symmetry or a center of symmetry like this molecule, for instance, then you'll find when this molecule is achiral. Its mirror image will going to be superimposed, right, to each other, or superimposable to each other. You can try, right? You can try to draw the mirror image, right? And then if you rotate, right, you will find these two are exactly the same. So this molecule doesn't have any denture. So that's why this molecule is achiral. You can maybe think about, right, rotate. Right? And this will give you 생각해 보세요. 그죠? 돌리면 똑같아질 겁니다. Okay? And we discussed the diisomers, right? Again, defined as a non-mirror image stereoisomers. And as we discussed, the possible, right, the maximum, right, number of stereoisomers to n, right? But if you have like the major compound, but then the stereoisomers, then the maximum number will going to be smaller than this, right? This is the another structure you can identify, right? All four different stereoisomers. What this case, right? And then you can assign cis versus trans name as well. Right? So you can imagine you have a general structure like this. That you can identify two asymmetric centers. Right? So maximum possible numbers, the stereoisomers in this case are going to be 4, right? In this case, no major compound will identify. So you will get 4 different stereoisomers, right? What about the bottom case? Right? You have 1 bromo-4 methyl, so you have this case, right? In this case, you only have 2 achiral diisomers, and then you can think about, right, in this particular case, right? You can think about, right, this, whether this side is the asymmetric center or no, right? In this case, no, right? That's why you only have 2 stereoisomers, which are diisomers to each other. 그래서 분자 구조를 보시고 이제 이렇게 asymmetric center가 존재하냐 안 대칭 구조를 보시면 어사인을 하실 수 있을 거예요. 1, 3의 substitut가 있는 경우에는 두 사이트 모두 asymmetric center가 되고, 그래서 2의 2승 안에는 4개가 이제 나온다는 얘기고요. 밑에 같은 경우는 고려를 해보면 asymmetric center가 이제 2개가 배제가 된다는 이야기. 그걸로부터 이제 결국 2개의 achiral type estromor가 어사인 해질 수 있다. 그래서 이거는 한번 연습을 해보시면 될 겁니다. 대칭 구조를 조금 그려보시고요. asymmetric center가 맞나 안 맞나, 그렇죠? substituent 4개 기준으로 봤을 때 2개가 완전히 동일하면, 그렇죠? asymmetric center라고 분류가 될 수가 없겠죠. We also discussed major compound, major isomers. And this is the example a major compound which all contain the internal right plane of symmetry, right? You can imagine there's a plane of symmetry making these two are exactly same, right? In this case, you won't get any mirror image, right? The mirror image to this it will be exactly same to the image one. Right? You can also assign the plane of symmetry here, and you can also apply this to the future projections as well. Imagine there's a mirror plane here, and even for the cyclic compound, you can imagine there's a mirror inside. And you can identify these two are exactly the same. So that's why this is all major compound, and they won't have any right, inertia. And you can tell right if you have like this conformer state, right? Then you can think about you can rotate right, with respect to a single bond, right? Then you can identify this as a major compound. And if you have the future projection like this, then you can think about there's a plane of symmetry. This are same. Right? So you can identify that this is one major compound. And you can then perhaps say these two are enantiomer to each other. Right? And this is again the cyclic compound, the exemplary case. And you can think about right whether this has the internal right, plane of symmetry here and there. Right? That's why this is major compound. But in this case, you don't have an internal plane. Right? This metal and this metal cannot be the mirror to each other. Right? So this will going to be eventually right, mirror right, to each other as a molecule, right? Not inside. Right? So this is a pair of enantiomer to each other, and this one is same. There's no internal right, plane of symmetry. Rather, right, the molecule itself is a mirror to each other. So this is why it's a pair of enantiomer, right? So you can think about again, right? You have the cis-1,2 dibromocyclohexane. You can identify right internal right symmetry, the plane of symmetry. Right? And you may think right, cherry conformer doesn't have plane of symmetry, but once right any possible conforming state, they have plane of symmetry, then you can treat it. This is a major compound. Right? Same thing for the 2,3 dibutane. You can think about eclipse versus stagger. Stagger one doesn't have right the plane of symmetry, but you think about eclipse conformer. At least one conformer has the plane of symmetry, right? Then you can treat it. This molecule or this configuration is major. Okay? So molecule become achiral when they have at least one right? Achiral conformer. Okay? 그래서 뭐 이렇게 구조식이 주어졌다. skeletal structure formulation으로. 근데 이 경우에 plane of symmetry가 사실 체어 컨포머를 그려보면 없는 거 아닙니까? 이렇게 물어보실 수 있는데 이 경우에는 both 컨포머를 생각해 보시면 plane of symmetry가 있다라고 생각하실 수가 있겠죠. 그냥 주어진 skeletal structure 혹은 뭐 분자식 구조에서 plane of symmetry가 identify 되시면 major compound이라고 진단을 내리실 수가 있을 것이고 그렇다면 이 분자가 가지고 있는 다른 스틸과 아이소모와는 아이소모릭 관계가 되겠죠. 이 매조 구조가 매조 configuration 그렇죠. 그렇게 생각하시면 되겠습니다. Okay. You can also think about the stereochemistry of the ammonium salt, right? Which has 4 different bonds. Right? So you can apply right the same rule, same system that we defined for R versus S, right? In this case, you can also think about then, right, the enantiomer relationship. You can define R versus S. Right? You can also apply for the phosphine oxide or phosphate species. Once the central right atom has 4 different arms, right, then you can still define right the asymmetric center to that entity. Right? And then in this case, you can rationalize right these two are the enantiomer to each other. Right? What about this one? This is is called the nexene, right? Name of this molecule, functioning for the inhibition, right? The proton pump inhibition, right? And you can perhaps identify, right, 4 different arms, right? And this surface site, right? The surface site is going to be the asymmetry, right? And perhaps you can identify, right, the R or S system. In this case, you have the lone pairs. It's a tricky case. You need to know, right, how to define R versus S in this particular case. The point here is this surface site is serving as an asymmetric center of this lone pair. Okay, so you have 4 different arms. 1, 2, 3, 4. 그래서 lone pair가 있을 때는 그러면 lone pair의 prior는 어떻게 됩니까? 모르셔도 됩니다. 그렇죠? 물어보진 않을 텐데 포인트는 surface site가 이런 경우에 4개의 다른 arm을 가지게 되면 asymmetric center의 기준을 만족하게 되죠. 테트라헤드럴 구조에서 팔이 4개가 다르면 asymmetric center가 무조건 작용하게 돼 있어요. 구조상. 그렇죠? asymmetric center를 우리가 사인할 수가 있다. 그렇죠? 그래서 카본 컨테이닝 카본 센터뿐만 아니라 암모늄의 경우에는 나이트로젠 사이트, 그리고 포스핀 혹은 포스핀 옥사이드 베이스 시스템에서 인 사이트, 그렇죠? 포스포러스 사이트도 asymmetric center로 작용할 수 있다. 그렇죠? 동일한 원리를 적용하시면 되겠죠. 구조적 유사성이 있는 거니까. Nomenclature, right? Same thing, but as we define, right? You can just assign the absolute configuration for, right, each asymmetric center, right? And just using the parentheses and call out the information there, right? The absolute configuration S R for each carbon, right? Then you can finalize the full name of that. Right? So once you have, right, this specific configuration and ask you, right, it can ask you, right, call out the full name, then you should be able to call out the absolute configuration as well. Just 3-bromo 2-butanol is not sufficient. Right? You have to assign absolute configuration, right? If your structure has a particular stereoisomer case. Okay, perhaps you can practice with the example below, right? And you can match perhaps, right? This is 3-bromo 2-butanol case, right? Given in perspective formula and in future projections. So you can perhaps double check, right? Each talk to each other, and each is asymmetric center sign correctly, right? S versus R. And then you can define, right, the relationship among these 4. Which one is the enantiomer, which one is diisomer to each other, right? 그래서 perspective formula와 visual projection을 왔다 갔다 하실 수 있어야 돼요, 그렇죠? visual projection은 저희가 어떻게 정의가 됐는지 기억을 하신다면 가능하실 거예요. 그래서 좀 연습을 해보시면 금방 패턴이 익숙해지실 거라 그렇게 어렵지 않을 겁니다, 그렇죠? 연습 나 하기 싫다. 그냥 데피니션만 외워와서 시험장에서 빠르게 적용해서 잘 돌려서 맞춰보겠다. 그것도 가능합니다. 그렇죠? 이제 연습을 하기를 추천을 드려요. 6.2 수업 들으시면 6.2 수업도 들어야 되잖아요. 그죠? 6.2에서 다 쓰게 되는 기본이니까 충분히 연습이 되시길 바랍니다. Okay, we can also think about physical properties. Physical properties of stereoisomers. I guess this is the last section for stereoisomers, I guess. We still have 10 minutes. And here we are defining the optically negative versus optically active. Right? And we define, right, the enantiomers which have the identical, right, chemical and physical properties. 거울상의 성질체가 동일한 화학적, 물리적 성질을 갖는다. 그렇죠? 이 말은 아마 다들 들어보셨을 겁니다. 그렇죠? 근데 거기 exception이 있어요. polarized 빛, 방향성을 가지고 있는 빛과 interaction 할 때는 다른 양상을 띠게 돼요. 뭔가 방향성을 띠고 있는 어떤 엔터티와 교류를 하게 될 때는 방향성을 띠고 있는 물체가 반응을 하게 됩니다. 다른 정도로. 그렇죠? 방향성이 없는 물질 혹은 액체와 인터랙션을 할 때는 두 개가 차이를 보지 않아요. 근데 방향성이 있는 물체가 방향성이 있는 무언가와 인터랙션을 하게 될 때는 선택성이 생깁니다. So enantiomers have identical chemical and physical property except in their interaction with the chiral species, chiral substance, or chiral entity. And also the plane polarized light. Plane polarized light, meaning it has the light has a directionalities. So integers will have different response with the chiral substance, right? That's the point. What is the plane polarized light? Or in short, you can just call it the polarized light. It's a light that has a electric vector that oscillates in a single plane, right? Not a multiple plane. And plane polarized light arises from passing ordinary light through a polarizer. So you have polarizer looks like this. There's a small slit, right? And then only the single plane, right, oscillating in this direction. Right? This is the electric vector of the light. Only this light can go through, right? This polarizer. That's how you can create, right, the plane polarized light. Right? Normal light will have all direction. But if you have a slit or a polarizer, right, and after passing through this polarizer, it will create this plane polarized light, and for which you need a polarimeter, right, to measure the degree to which the organic compound would be respect to this plane polarized light. Right? You have some chiral molecule, right, and you can imagine this plane polarized light will have some interaction between, and this will tilt, right, the angle of this plane. And you can measure that angle using the polarimeter. 그래서 아직 합성 실험 수업 안 들었죠? 2학년 때 이런 학생도 있을 거고, 고학년 학생들은 이제 합성 시험에서 이 polarimeter를 이용해서 실제로 얼마만큼 폴라라이저를 통과한 이 polarized light이 chiral molecule과 interaction 했을 때 돌아가는 그 앵글을 재게 되어 있는데 그 앵글을 잴 수가 있어요. 별로 복잡하지 않습니다. 소스 있고 폴라라이저 있고 그리고 몰레큐 카이랄 몰레큐를 위치시킬 수 있는 섹션이 있고 빛이 지나가면서 이 폴라라이즈 된 라이트이 앵글이 돌아가게 돼요. 인터랙션을 하게 돼서 카이랄 몰레큐로 그 앵글을 그냥 잴 수가 있어요. 그걸 재면 이제 얼마큼 카이랄 캐릭터인지 이야기할 수 있는 척도가 돼요. 뒤에서 조금 더 이야기하겠지만. Okay. So again, point is the chiral molecule. It actually will have the interaction with this polarized light. Right? And in general, right, chiral species will have interaction with the chiral substance. Right? If an entity has some directionality, they'll have interaction. Right? And this is the how the set will look like. So you have light source, polarizer will create polarized light again, right? And you have a sample tube, right, in which you have you can have the compound or molecule, right? Double case you have a chiral compound, bound case you have the chiral compound. And chiral compound will have interaction with this polarized light specific way, and this will rotate the plane of the polarized angle. Right? Whereas the asymmetric molecule, they won't have interaction. The plane of polarization will just remain. There will be no rotation. That's how you can define optically active versus optically inactive. Achiral compounds, optically inactive, meaning there's no rotation, right? Plane of the polarized light doesn't change, but the chiral compound, right in the sample, they can interact with this polarized light and tilt the angle, and plane of polarization get rotated. And you can measure the degree to which, right, the polarized light rotates after interaction with the molecule, right? And you can measure the angle alpha in degree, right? And you can define this as observed rotation. Okay? And this is somewhat actually looks complicated maybe at first sight, but it's not, right? You can define optical rotation measured with the polarimeter gain. And first you should define the optical activity, right? A here, A in parentheses, right? And you can define here the L and C here, and here's the scheme for the sample order. You can imagine there is a length scale, right, of the sample, L given in EM, right? And you have the concentration of sample in the sample order, right? Given in this case gram per milliliter, right? And then if you normalize, right, the angle you measure, right, the real angle measured by the polarimeter, and normalize by this too, right? The length scale times concentrations, then you can get this specific, right, rotation angle, right? So that basically you can think about you're normalizing, right, the raw value, the rotation angle in this case, right? And then you can perhaps measure, right, the rotation angle of this molecule, which has R absolute configuration, and it's in enantiomer, right, S, right, containing S absolute configuration, and then you'll get, right, the same magnitude of rotation, but the sign is different. Right? So in this particular case, R isomer give you 5.75 specific angle rotation. S will give you minus 5.75 rotation. But it doesn't. It is not always the case. R give you plus and S give you minus. Right? It's a random, right? So you cannot predict, right? But you know that once the R give you plus, then S will give you minus, and vice versa. If S give you plus, then R must be minus. 그래서 아주 어려운 컨셉은 아니죠, 그죠? chiral species가 chiral species로 반응한다. interaction 한다. chiral 분자가 따라서 polarized light과 interaction 한다. 그래서 polarized light을 돌게 만드는 거, rotation 하게 되는 거예요. 플레인은 polarized light의 그 평면 각도를 돌리게 되고 S 혹은 R absolute configuration을 가지고 있는 이제 zero isomer가 특정 앵글 값을 주겠죠. 그러면 R 폼이 준 앵글의 정반대 부호의 같은 크기만큼의 로테이션을 그 이네슈어머가 주게 된다. 그렇죠? Almost done, but we can perhaps define this term and we can finish next time. You can define, right, enantiomer axis, right? It's called EE, right? This is defined as the difference between one to the other, right? In percentage, right? S minus R or R minus S, right? Then just simply applying this definition, you can get the following, right? And there is another term, the enantiomer ratio, right? And you should be able to convert, right, the ratio and EE, right? ER and EE can be interconverted, right? So 80% of ER meaning 60% of EE for one nature. Okay? So it's a simple relationship between enantiomer axis and a sort of specific rotation as we defined in the previous slide. And of course you can measure, right, the specific rotation of the pure enantiomer, right? And you are measuring the mixture, and by getting the ratio in percentage, you will get the axis. Right? And here's some example you can apply the definition to get an answer. Right? So maybe we can revisit next time here, and then 그래서 뭐 사실 여기 나오는 수식들은 게 복잡한 건 아니에요. 한 번만 이제 적용을 해서 문제 한 번만 풀어보시면 바로 감을 잡으실 텐데 이제 얼마만큼 앵글이 돌아갔냐, 이제 퓨어한 이제 이넨슈어머에 돌아간 앵글 대비 우리 어떤 케미컬 합성이 있으면 아주 퓨어하진 않을 수가 있잖아요. 믹스처일 수가 있죠. S랑 R이 어느 정도 섞여 있을 수도 있고 대부분의 경우가 그렇겠죠. 그 경우에 그러면 믹스처가 가지고 있는 믹스처 샘플을 가지고 저희가 로테이션 앵글을 재고 알고 있는 퓨어한 이넨슈어머의 앵글로 이제 나눠주게 되면 이제 얼마만큼의 한 이넨슈어머가 더 엑세스만큼 존재하게 되는지에 대한 정보를 습관적으로 생각해 볼 수가 있겠죠. 이제 수식적으로 이제 ER과 EE를 저희가 따로 적용하게 되는데 80% ER이면 60% EE가 된다. 이거는 아마 단순 수학이라서 쉽게 반응하실 것 같은데 다음 시간에 이어서 한 번만 더 요즘 마무리하고 아이템 챕터로 바로 넘어가도록 하겠습니다. 아이템 챕터는 상당히 쉬운 내용이